way. The first two we're given. Obviously, it's very, very straightforward. HI is 9, IJ is 9. Why is HI equal to IJ? They're both the same. Now, when you look at your reason bank, now take out your reason bank also. You should have your reason bank and your progression sheet, because we're going to bounce back and forth on those today. Add a couple of things to both of them as we go through. On your reason bank, we have something here called substitution. Substitution is basically when two things equal the same thing, they equal each other. Substitution is when two things equal the same, then they equal each other. Okay. Substitution is for when two things equal the same thing, then those two things are equal to each other. Okay. Whereas on your reason bank, probably on the bottom, I know that we wrote down something else. We had something at the bottom on their first day we had it was A equals B, and B equals C, then A equals C. Do you remember what did we call that? Should be on your reason bank. It is the law of syllogism, correct, but we called it something else on the reason bank. Not just real numbers. No. Third time's the charm.
Transitive property of equality.
Perfect. Reason we called this the transitive property. Okay? We called that the transitive property. Whenever there's something that has that diagonal component to it, where it's repeated on a diagonal, that was the transitive property. Substitution, on the other hand, looks a little different. Substitution is going to look like this. I use A's and B's, so we'll use X equals Y, W equals Y. What can you say?
That X equals
And that's it. And that's the substitution. That's what substitution looks like. It's a little bit different. Transitive, there's a diagonal component. Substitution, they're usually written right above one another. Okay? I'm not going to lie. Substitution is probably one of the most widely used reason in any proof. Okay? So if you're drawing a complete total brain fart and you have no flippant idea what it is for your reason, and you're going through all the different ideas that you might have, it's not the worst idea to guess and put substitution in. Yes, sir? Oh, thank you. I just saw that. Thank you. Yeah. I saw that Y and just kept writing it down. Okay. All right. So a lot of times within proof, someone asked me this yesterday also. Is it possible within a proof to use the same thing more than once? Yeah, absolutely. Absolutely. You can reuse reasons. There's no set limit to how many times a certain reason can be used or anything like that. It's all kind of up for grabs. It all depends upon the type of problem. Now, as we get into like actual triangles and things like that, there's a certain style or certain nuance within them that you'll start to pick up on, that it's kind of the same thing over and over again, because it's just letters that are changing. But the process to which they set up is the same. What we start with here with these segment ones and these very little subtle substitutions and whatnot is get us ready to do the more complex ones later. And I know, I'd probably say 95% of you guys had no flipping idea what you were doing last night when you tried to do these two. And that's okay. It was the first time you've ever seen them. And it takes some time to get used to. And that's what we do. We go very slowly into this, so that way when you get going, you're going to be fine. Okay? The past couple times that I did it, this method of taking our own sweet time to go through these things and write these progressions out, I'm not lying to you. If you trust these sheets and you write down what we're going through, and you go through and follow the procedures, you're gonna be really successful when you take those first quizzes, okay? I think the test that I had that was proof-based in triangles, that when we did it after a couple of years in a row, we were getting B averages, guys, because all your answers are on that sheet. You just have to find it. Everything's there. It's like the world's greatest note card. It's just bigger. Okay. So back to this one then. HI is 9, IJ is 9. Why is HI equal to IJ? Exactly. It's substitution. And now comes the weird one that we ran out of time for yesterday. This one I want to put in a square. One thing that you're going to notice a lot of times with proofs and with segments and angles and all that, when you deal with segment addition or angle addition, it's all dealt with in terms of equality. Angle plus angle equals larger angle. Segment plus segment equals larger segment. It doesn't say segment plus segment congruent larger segment. It says equals. So sometimes within proofs, you have to switch between an equal sign to a congruent sign, or vice versa, okay? And it's a very, very subtle thing. So what we put in our square is to switch between equal to congruent, or congruent to equal. We do the following. And I'm just going to do the two separate examples here. Let's say AB equals BC, and that's given. In order for us to switch it to congruent, our reason is, this is a real tough one. Definition of congruency. That's it. No, it's sarcasm. So in order to switch, because remember, if things are equal in measurement, they're congruent. And if things are congruent, they're equal in measurement. That's just a very subtle way to switch back and forth. So a lot of times you'll see that you start equality, but at the very end they're talking about congruency, especially with segments and angles, because it's one extra step that they're trying to get you to do. That's all that means, guys. That's all that means. You're just switching it. And then it means the same thing going the other way. Or, let's say we had x, y equals yz. Oh, I'm sorry, congruent. And that was given. If I wanted to switch it to equality, all I would write is xy equals yz. And what do you think my reason is again? Definition of congruent. It works for both of them. Okay. It's the same thing for both. All right? So it's a very subtle switch. Sometimes given statements will talk about, x, y is congruent to y, z, but then they're going to want you to do segment addition later on. Then it means in order to do segment addition, you have to have it in equals. That's all. Additions, segment additions, angle additions are all within equal. So you might have to make this switch. Okay? Does that make sense? Now, they call it, the technical term is, well, if you're dealing with segments, it's definition of congruency of segments. If it's angles, it says definition of congruency of angles. For me, I don't care. Definition of congruency, I'm happy. I'm making it easier on you. Yes, sir? I couldn't hear you. What? What I'm saying, yeah, no, that's okay. Because sometimes you're starting with congruency, you got to go to equality to do an addition problem. It's the subtle way that you switch between it. It's just a one step definition, congruency, and go. Okay. It's a very, very subtle thing. All right. Is that okay?
So the top one's a subtraction and the following?
No, it's either one. Okay. It's the same thing. All I'm saying is that if you're starting in equal and you have to go to congruent, the reason is definition of congruent. If you start in congruent, you got to go to equal. The reason is still definition of congruent. You use the same reason for both. It'll make more sense if I show you this. Well, actually, the example that they have here makes a lot of sense. So here, notice they say definition of congruent segments. That means that they have then HI is congruent to IJ. That's all it does. Because look at the next two parts. They're all incongruencies. They just switch from equality to congruent just to keep the flow. Also, notice how they start putting the technically you're supposed to have a bar over the segment when they have congruency. Do I care? No. I do. But no, I really don't. I'm happy you wrote down the right part. That makes me happy. What?
Never mind.
Good answer. No, what's up?
No, never mind.
No, I'm not going to harass you, maybe. What do you want?
So how do you know this congruent?
What do you mean?
She said you don't care if you have that first two.
Oh, and not the squiggly part. I mean the bar above the segments. See how they have like HI.
Wait, you don't care if it's there?
I don't. That little bar piece there. No, I really don't. It's supposed to be there if you're in congruency, and it's not supposed to be there if you're in equality. I don't care. Really? If you guys are getting through all of the proof stuff and you're putting everything in the right progression, you're getting everything correct. Do I care if you put a label on the top of it? No. Do I care if you forget to put the angle symbol in front of something?
Yeah.
Well, of course, that. Do I care if you use 3 letters for a segment?
Yes.
Yes, because you can't. Little things like that. But this part here, whatever. Not the end of the world. So, now going back into this, the next step, if you read the problem again, was what? No, we're going to do all this. We're going to add more to it. What was the next step then?
Isn't that,
What is it?
is that syllogism?
No. Look at it. What is it? What is it?
Given.
It's given. We hadn't gone through all the givens yet. Thanks, sir. We hadn't gone through all the givens yet. So there's your next one. It's given. Sometimes they do this. The book will tend to split up givens. Personally, I try not to. If I have a given statement, we'll do an example of one like this in a minute, where I will work the given statement and I will do everything that I can off my progression sheet from that given statement before I go to the next one. And you'll see that when we have one here in a minute about midpoint. Okay? So now look at what they have. They have HI congruent to IJ, IJ congruent to JH, HI congruent to JH. You said this earlier. What is that? It's not substitution. It's syllogism, but when it's written out in a proof, we don't call it the law of syllogism. We call it starts with a T and ends in a transitive. The transitive property. It's transitive. Okay? The transitive property, because there's a diagonal component there, and you're done. So when you have law of syllogism, which this is, in a proof, we call it the transitive property. Okay? That's how that works. Meh.
The more you know.
Let's write another one.
Does that mean that we're not going to turn this on?
Well, this is the first day of doing proofs. I don't collect a lot of stuff when we first day of things, and it's just, there's no reason, because half the people didn't even try to do this. Because you guys would say, I don't know what I'm doing. So we start slow. Same deal. Same deal. When we start one like this, move this out of the way. When we start one like this is going to be, we're going to be able to utilize a progression. Because on our progression sheet, we have something about complementary angles. What do we have on our progression sheet about complementary angles? What?
Equals 90 degrees.
What equals 90 degrees?
A complementary angle.
No, they don't.
Wait, it's 2 angles equal.
What does it say? Start over.
Two right angles.
What does not say that? What does it say on your, look at your progression
It says
sheet.
angle plus angle equals 90.
Look at your progression sheet. That's not your progression sheet. When you have complementary angles, what does it say? That's not what it should be. It should be angle plus angle equals 90.
Yeah.
Just right, make sure it says angle plus angle, not complementary plus complementary. Angle plus angle. So if you're given this, then you state two angle plus angle is 90. Well, in this case here, we have angle 3 and angle 2 are complementary. That's given to us. That was given to us. Yeah, according to our progression sheet, according to our progression sheet, it says angle plus angle is 90 is what you would say after you're given complementary. Well, what are the two angles that we're given here?
Angle 1.
3 and 2. Oh, they skipped to here though. Notice what they did. They put their two givens right next to each other. If it were me, I would have said something about 3 and 2 right away because I have that on my progression sheet. Does that make sense? So I'm just going to kind of skip ahead and go to the third line. Why are 3 and 2 add up equal 90? What's the reason though on your sheet? What does it say to say? Definition. Okay. When I do proofs and when we start to do proofs on our own, this is one of those examples that I would ask you guys to utilize everything you can from that first given statement prior to going on. I know I've got complementary angles. What are they? 3 and 2. So that means 3 and 2 have to add up equal 90. I just have to skip that step, that second step that they have here. Because what is that second step according to this? Given. It was given.
Oh.
Okay? Now, look at what they did to get to the fourth step. Why is angle 1 and 2 equal to angles 3 and 2?
Oh, it's a substitution.
It is substitution. Very good. It's substitution because don't they equal the same thing?
Yes.
So when two things equal the same thing, they are then equal to each other.
Oh.
There's your substitution step.
Oh, and it's substitution.
Yes, sir?
And that is the next one, substitute.
What was it?
Substitute properties.
No.
It's not?
You said substitute property?
Yeah. Yeah.
Is there a substitute property equal?
Substitution property.
Oh, we already did substitution there, but take a look. Look at here. Are those the same on both sides of the equal sign?
Yes.
Subtraction property quality. Because look what happens when you go from step 4 to 5.
Oh wait, no, that's what I meant. I put subtract. I just said it wrong.
That's what I thought, because you were saying property equal. That's why I wanted to make sure what you had there. So, yes, it is subtraction property equality. Because you had angle 2 on both sides. If you subtract angle 2 from both sides, it stays equal because you did the same thing. So you're left with sub T prop equal. Okay? Put it in your pocket. You don't need it out. I mean, it's one thing if you're halfway in the back, but you're right in front of me.
Wait, how's it say?
What's my next reason? Definition congruency. You don't have to put the angle part in there. I'm okay. If you just write definition congruent, that's fine. If you wrote definition congruent angle, that's also too. That's fine too. Okay. Your last step, notice, the only thing that changes is they throw a congruency symbol in there. Squiggly showed up. Final answer? Okay?
That's my name.
That's all it is? Okay. That's all that is. Now, I got a couple more things to add into squares and stuff like that, but I want to start with the next proof. Let's draw this one up. Let's do this one. We need to we need to work on another style proof. Another style proof that we have to go over another definition that we haven't looked at yet. So throw this in your notes wherever. I'll tell you. Remember, I'll tell you when you're going to use your sheet when we're going to put something in a square. Okay, so back to this. A lot of times when you're dealing with proofs, you want to spend a couple of seconds looking at what they give you, what kind of a diagram you have, and what they want you to show in the end. If you take a minute or so just by analyzing that information, it's going to help you to figure out the direction that you should head. It'll help you to decide whether or not you're going to be doing some substitution. It'll help you to decide if you do segment addition, angle addition, something along those lines. Now, when I'm looking at this problem, it tells me that I have AL is equal to SK. And then it wants me to prove that AS equals LK. First thing, do you think that we're going to have to do any definition of congruency to this problem? Just switch in or out of equality? Usually not. If it starts the problem in equal and it ends in equal, you're probably not going to use that step. Okay? But take a look at the information that they're giving you. They gave us that small chunk AL and the small chunk of SK. We know that they are equal in value. So I know I can throw a tick mark on that. Okay. After that, I also know what they want me to prove. They want me to prove that the segment AS is going to be equal to the segment LK. Well, in order to do that, do those two segments have some sort of common overlap? Yeah, what is it? What do they have that's common overlap? LS. LS is in the middle, it's in the middle of both of them. LS is this value here. It's this chunk, okay? Now, if you just think about it, if you have,
I'm thinking,
no, go ahead, go ahead.
can you do AL and SK and I combine them together to do
AL and SK.
Yeah.
You're on the right track.
See, I'm like thinking,
But notice, isn't AS is made up of AL and LS, isn't it?
Yep.
LK is made up of LS and SK. So the two larger segments are made up of two smaller segments. How do you write, what property or what thing tells you that you can add two small segments together to get a larger? Segment addition. I'm adding segments together. Segment addition says segment plus segment equals larger segment. That's what that looks like. Now, in this problem, anywhere here in the given, does it define, does it say that LS is there? No. No. So, but it's in the diagram. Obviously, does everybody agree that we're going to have to add LS to AL and LS to SK to make the larger segments?
oh yes.
When we start to think like that, we have to remember that in math, in order for something to be used, you have to define it. You have to say that it's there. How we say that something is there is that we use, and this is on your reason bank, what's called the reflexive property. The reflexive property basically says you are yourself. That's it. The reflexive property says, and you can probably put this here, you are yourself.
It kind of sounds like reflective.
Exactly. But reflective is more of a symmetric property because it's the same thing back and forth. So we use this to define something is there. We use this reflexive property to define that something is there. A lot of times, we use this in segment addition. Bless you. If you have two smaller segments and then you have to add it to the same overlap, you're going to have to use it. Same thing with angle addition. Sometimes you might have an example where we have where you have this angle here, angle 1 and angle 2 are congruent already, and then you want to show that these two angles are the same by adding in this angle 3 to both of them. You have to define that this angle is there. Same idea with segment stuff. It's the same style, okay? So a reflexive property, you use it to define that something's there. So hopefully you wrote that on your reason bank by reflexive property, because that will help you remember that it's there. Go figure. Who is he? Yeah, you know, I forgot my screwdriver at home. Okay? So, where do you always start your proofs? On the given, which means I would be starting on the left, going to right. Sure. I mean, we can do it this way.
That was cool.
You know how hard that was to do?
It's like how it is in China, don't they?
Did I spell
It's really hard to do that, okay? So I started with the obvious. I started with my given. Okay? Now, in that time that we took a second ago, just to kind of look ahead to where we need to show something, we all came under the agreement that in order to prove that AS is going to be the same thing as LK, we have that middle overlap. That middle overlap of, what is it, LS. But in order to use that, we have to say that it's actually there. This is where that reflective property comes into play. So what I have to do then is write this. LS equals LS. And the reason that it equals itself is the reflective property. Is that what I called it? Yeah, reflexive, sorry. Reflexive. Reflexive. You are yourself. Ouch. You must have really deserved that one.
No.
Okay, so now let's think of it in terms of segment addition. Or addition property of equality. If I think about it, addition property of equality, that basically says if you add the same thing to an equal sign, it stays balanced. Do you agree?
Yes.
Now, since we know that LS is still the same thing as LS, if I add it to here and here, doesn't it stay balanced?
No.
Yeah,
But there's different stuff on each side.
But we know that those two things are the same. So if we
Well,
think
then
about,
it's
well, it should be, because we knew, if this is this true?
Yes.
Is that true?
Yes.
So if I do this, is that true?
Yes.
Because I added the same thing to both sides, which continues to give me a true statement. That's how that works. Even though the letters are different, since we were already told that they are equal to each other, we can do that. So, come on guys, if I add the same thing to both sides of the equal sign, I use the addition property of equality. Add prop equal.
That's your letter reading?
Yes, sir.
I'm like at school and you're teaching me, it's so easy when I get home. I just like, I'm just.
Hey guys, I'm not gonna lie, it's gonna get easier. It really does. You've done this for a day.
He's lying.
Proof stuff's only been a day. Okay. I'm not lying to you. It takes some time to get used to it. Yes, ma'am. Yes. Okay. it takes time to get used to it, all right? And I don't expect you guys to be perfect at this after 2 days. That's crazy, okay? So now, look at what we can do. What is AL plus LS equal to?
But you just subtract.
What is AL plus LS equal to in our diagram?
Oh, A.
It's AS, isn't it? AL plus LS is
Oh, AS.
Oh.
AS.
Okay, I thought I was.
What is SK and LS equal to?
What did you say?
Okay.
What did you do? I added what? I added 2 segments together to get a larger segment. What is that?
Oh, that's the
Set
whole thing. Wait, that's
Very good.
That's segment, yeah, segment addition.
And is it okay that I did that in 2 spots? I don't have to write it twice?
Yes.
It's fine, because I did the same thing. I used segment addition to rewrite that. Because I know that 2 smaller segments make up a larger, especially, obviously we know they're collinear, I don't have to worry about that. But that's how these things work. You slowly build yourself through them, okay? You have to get to the idea that you can define something that's there, and you just wind up adding it to both sides, okay? Then, all right. Let's do another one. This other one that I have for us it deals a little bit more with a little bit better of a progression. It's more of a,
That's from the tree.
yes sir.
When we have to solve. One of the steps solve.
No.
You know,
Usually solved is never a response that you're going to use when you're doing a geometry one. Algebraic ones when you have solved. When you know that x equals something. Okay. The geometric ones, you're showing that something's congruent to one another, or something was equal to something else. In this case, we're showing that something is equal to twice something else. So we're going to use some algebra properties with this. Don't think we'll have to use solve if we're not solving for a specific value. Okay. So let's use one with midpoints. If you guys look, you know you have midpoints on your progression sheets. We did that one. We wrote that one. I think it was our very first one that we wrote out too. Okay. So take a second, write this one out, and what I want to do is draw the picture, mark our diagrams, and walk through how do you actually go off of 2 givens into the relationship with them with the progression sheets. As we get used to this, it's going to be very easy to bounce back and forth. And I'm not going to lie to you. Pretty soon, you know, the next couple of weeks or so, as we get through more of these, you probably won't have to look at your sheet about what to do when you see a midpoint. It's going to become second nature because you know that a midpoint creates equal segments. Yes? Do what?
Why am I so good?
She said seven. It's like, why can't it be 2 dimensions? What?
It's gonna be really fast.
Wait, does that say MB equals 2 MB?
Yeah.
What is 2 MB?
MB plus MB. What is multiplication? What is multiplication? Is it multiplication just repeated addition?
Yeah.
Because what's 2 plus 2 plus 2 plus 2? 8. 2 times 4. It was 4 groups of 2. So 2 groups of this segment NB is just MB plus NB. That's all that means. And I'm going to explain that in a second. Bless you. I'll explain this for you in a second. Okay? So when we start this one out, we have midpoints. We have that M is a midpoint of the segment AB, and B is a midpoint of segment MD. So just by starting with our very first given, we always write that down first. And then we'll go back and mark our diagram and see what we can find out from there. So in here we start with our good old-fashioned 2 columns. I have M is the midpoint of AB. Oops. and that's given. Now, according to your progression sheet, what is your next step after you're given a midpoint? What does it tell you you are supposed to do?
What sheet?
Progression sheet, squares. On the squares, one of the things that you have, the first one we ever wrote out was about midpoint. It told you to do what?
What's that thing?
Segment equal segment. So knowing that M is the midpoint of AB, that tells me that I have to now write down what segment equals what other segment.
Oh,
AM equals MB. Notice I went right to my diagram and I marked them up. Okay? I marked those two up. According to my progression sheet, guys, according to my progression sheet, after I have a midpoint, it tells me what segment is equal to what segment.
We just go in order of the line, right?
Yes.
Alright.
AM is MB. The reason that I can say that is because we just used the definition of dun dun dun.
We should make a theme song.
If we made one,
No, just because you can rap on piano.
Oh, you're
Now-
a fan. You said
No, I
it.
just saw it.
Oh, yeah, I see that. Okay.
Anyway, have I done everything that I can from that first midpoint
Yes,
statement?
that's it.
That's it. So now I go to my next given. My next given says now that is B is the midpoint of MB. That's my next given. So knowing that midpoint tells me that I have to state the two segments that are equal to each other, I need to go to my diagram to figure out what two segments I need to mark. Well, B is the midpoint of MD. MB is one of the segments, and it already has a single tick mark, which means BD has to have how many tick marks? One. Because they're going to be equal, so it's also going to have a 1. Okay? All right? So I know right away, just by looking at my diagram, I know that these three chunks, they're all equal to each other because I've just walked through that part. I haven't proved it yet, but I have it in my diagram. Okay? So it told me, midpoint, now I write down my two segments. It was MB and BD. And that was the definition of a midpoint. Okay? It wants us to focus our attention at segment MD. If I go to my diagram, what is segment MD made up of? How can you write that?
MB plus
So MD is made up, bless you, MD was made up of what two segments?
MB and
Perfect, why?
because
What,
plus BD
what are you using? You're adding two smaller segments to make a larger one.
What's the segment?
Segment is.
That's it, that's it.
Second division.
So there's your segment division. Hey, look at what, we only have 2 more to go, believe it or not. Look at step 4 and step 5. Move this up there. MB equals BD. MB plus BD. It wants me to show that MB is made up of just MBs, which means, can't I replace this BD with an MB? By what?
Is that substitution?
It is something. It is substitution. I have two things that are equal to each other, which means I can replace them at any time. MB equals BD, which means anywhere I see a BD, I can replace it with that. That's all that is. Thank you. What do we do?
Sub.
Substitute. We put something in for something else. And then lastly, repeated addition is multiplication. The reason here is called the definition of multiplication, but I'm running out of time here, so I want to make sure I get you guys a couple of problems to look at. What I have here, and we'll write out how do you do definition of multiplication. We'll start with that tomorrow. Definition of multiplication is whenever you see repeated addition, that's just multiplying. That's all that means.
In Snowy Ball 12. Snowy Ball 12.
It was working at the beginning.
Oh, is it 12? What's wrong with that?
I'd reboot it, see what happens.
Is that your
But I like
dad?
sign out and then not even like sign it.
I'm not sure. So on this one here, there are, on the sheet that I just gave you guys, on the first 3 pages, on the first 3 pages, I want you to do the bottom problem on the first 3. So on page 1, do the algebra proof on the bottom. On page 2, I forget what that would look like. I think it was the second one. Yeah. Yeah, the bottom of page 2
The third one?
is a segment problem. I totally forgot to number these, so that's my fault. And then on page 3, oops,
Page 2.
on page 3, there's an angle proof at the bottom of the page.
So just the bottom of it.
I want you to do those 3. I want you to do those 3 fill in the blank proofs. Okay? You have 3 of them, ladies and gentlemen. The bottom of page 1, bottom of page 2, and the bottom of page 3. Okay? I will, in case you lose your sheet of paper, I will upload this document by the end of the day. That way you have it online as well in case you need it. Okay? But I hopefully won't lose it. All right? When we start, don't forget, multiplication is repeated addition.
Sing that to the top.
Adios.